Previously we talked about conductors, and now I would like to talk about insulators. In this context, we often use the word dielectric, which is a synonym for insulator. So dielectric equals insulator. And you might wonder, why would we have two terms that mean the same thing? So I think the answer really is in the fact that dielectric is a model for an insulator. So real insulators might do something complicated, but a dielectric is a particularly straightforward way to think about how these materials behave. All right, so in order to explore how insulators behave differently than conductors, what I'd like to do is imagine that we have a situation where there's sort of just an external electric field. Okay, kind of like this, so drawing some electric field lines. And maybe let's do 5. So I'll do 5 electric field lines like this, equally spaced. And let's start by thinking about how a conductor in this electric field would interact. All right, so let's say that I have a conductor which is some shape like this. Okay, and far away from the conductor, it's going to have this essentially constant electric field like I drew before. But as it approaches, the conductor is going to distort the electric field kind of like this. And so what we want is, as the electric field gets close to the conductor, it's got to be perpendicular to the surface. Okay, and then over on this other side, maybe it kind of goes like this, so that we end up with essentially the same electric field far away that we would have had without the conductor. So this, essentially uniform electric field. So how can we understand what's going on here? Well, we know that the electric field inside the conductor needs to equal 0. And what that means is that we're going to have negative charges where these electric field lines end, and then positive charges where the electric field lines start. All right, so this is just polarization in a conductor. We get this interaction between the electric field and the conductor, and then we end up with E equals 0 inside. That's the rule for conductors. Okay, now that's complicated because if a conductor has a weird shape, then typically we will have no idea what the charge distribution should look like in order to make the conductor have an electric field of 0 inside. Let's assume that the conductor has a really simple shape then. So let's say that we have a conductor that is just a block. Okay, so here's my conductor. And in this case, we're going to have the electric field be perpendicular to the surface, which is now easy enough to do because the surface is perpendicular to where the electric field would have been anyway. Okay, so it'll look something kind of like this, and then out the other side, kind of like this. Okay, and then if we have no electric field inside, like we're required to do, well, that means that there's going to be some negative charges over here where these field lines end, and there's going to be some positive charges over here where the field lines start. And then the electric field from those surface charges is going to cancel out the external electric field. Okay, so the electric field is 0 inside, and the reason is because we have the superposition. So for the green, the electric field lines are going backwards, again from positive to negative as they always do, but this time they're canceling out the electric field. So the blue one is going to be to the right, and then we get a total of 0. So just to write that out, we have E total is going to be E external plus the E internal, so the electric field from the charges. or sometimes we'll call this an induced electric field. So E induced. Okay. Okay, so how is that going to be different than what happens inside an insulator? Well, let's imagine that we have the same situation, but this time we have a dielectric. So dielectric. And the external field is going to look much the same. All right, so I'm going to, as we showed here, the electric field lines kind of go through, but then we cancel them. So I'm going to draw it that way, like this. Okay, and so we have electric fields pointing to the right here. But the dielectric is not going to be as good at canceling the electric field as the conductor is. So there will still be some charge that will separate. We talked about a model for that several chapters ago. But it will be less effective. So maybe instead of having every electric field line canceled, we'll just cancel some of them. Like this. Okay, so we'll end up with some positive charge on this side and some negative charge on this side, but just not as much. Okay, so here the electric field is not equal to 0 inside. There's still some remaining field. And in this case, the E total is still going to be the same. It'll be the external field plus the induced electric field. And in particular, I should be treating these as vector equations. So let me put in my vector symbols. Each of these is a vector. And because the induced electric field and the external electric field are opposite, if I want to think of this in terms of scalar quantities, then in fact it should be E external minus the induced electric field. Okay, because they are canceling out. Okay, so again, for a dielectric, those things are not canceling out exactly, so there will still be some leftover electric field inside, just weaker than it would have been before. Okay, so the claim then for how a dielectric will behave is that the induced electric field will be proportional to the external electric field. So if I double the external field, then I will double the induced field, which seems like a reasonable enough assumption. Okay, so what that means is that the total electric field will also be proportional to the E external and the E induced if E induced and E external are proportional to each other. So at the end of the day then, we get that the total field is going to be proportional also to the external electric field. All right, so we give a name to that constant of proportionality. We just call it 1 over kappa. So this is like a small capital K times E external. Okay, so to give you a little bit of explanation for what kappa looks like, if I just imagine, like, here's your writing line, okay, and here is a small k, a lowercase k, then kappa is just going to be like a small capital K. Another way people sometimes write this is you can do like this little wiggly symbol like that. So when I do kappas, I personally can tell from my own handwriting what the difference is. I just do it as a small capital K. If I want to distinguish that from a K, I make sure that my K has a long tail. Okay, so this constant, kappa, is called the dielectric constant. And it's just a material property, so you can look this up. You can look up dielectric constant for ceramic, the dielectric constant for various kinds of plastic, for glass, and so on. So it's just a material property, and you can find them on, Wikipedia and a variety of other places. One other detail that I want to mention about this is in various equations, if we're interested in a situation where a dielectric is present, we can often just take epsilon naught and replace it by kappa times epsilon naught. Okay, so for example, if we wanted to consider a point charge underwater, well, the electric field is ordinarily 1 over 4 pi epsilon naught times q over r squared. Well, if we want to consider what happens underwater, we can just take k for, or kappa for water, and plug it in there, and that will give us the electric field due to a point charge underwater. Essentially, the water interferes with the ability to create an electric field because the water will react to it. So these polarized molecules are going to orient themselves in just the right way. Because this shows up so often that we can just take epsilon naught and make it into kappa times epsilon naught, we give a name to kappa times epsilon naught, which is just epsilon. So you can think of epsilon naught now as the sort of, if there's no material present case. If there is a material present, we just use epsilon for that material, and epsilon is just kappa times epsilon naught. And so in this case, we call epsilon naught the permittivity. So epsilon naught was the permittivity of free space. Epsilon is just the permittivity. So you could, again, look up permittivity of water, permittivity of glass, permittivity of different kinds of plastics. And again, that's just a material property.